100,000 times, whatever the scientist is looking at on the computer screen, it's said to be magnified 100,000 times. Do you know the meaning of magnifying 100,000 times? That means 1 centimeter, which is this much, would appear to be 100,000 centimeters. How much is that in meters? 1 centimeter becomes 100,000 centimeters. So how much is that in meters? Take away 2 zeros, right? Divide. So that is
Kilometer.
no, in meters. You have to divide by 100. So you got, how much did you get now? You got 1,000 meters, which is 1 kilometer. That's what you meant, right? Wow. That's what you mean by magnifying 100,000 times. Many times we don't understand. You know, we just say 100,000. 1 centimeter just became more than 3/4 of a mile, just to give you the perspective. So that's what microscopes can do, especially an electron microscope can do that. That's why you're able to see tiny bacteria and tinier viruses. See, you can see all those things. So, but then we have to look at the human eye. And does anyone remember? I told you that the major part of the focusing is done by which part of the eye? The cornea. So when light passes through the cornea, 2/3 of refraction happens here. And the remaining 1/3 happens when it passes through the lens. So together you have the light rays being focused on the retina. Well, of course, you know that where the optic nerve connects to the retina, you call that a blind spot. You know that, right? All of you know that? Okay. So cornea does 2/3 of the refraction, and the lens does 1/3 of the refraction. What's interesting is the refraction by the cornea is fixed, is constant, but the refraction by the lens changes according to the distance of the object. So if you're looking at an object that is really far away at infinity, then you say that the eye is relaxed. So you have to know that term. When you say the eye is relaxed, that means you're looking at the stars. That means you're looking at distant objects. And you can remember it this way. It's always stressful for the eye when you're reading a book as compared to looking at the stars. So when the object is closer, the focal length of the lens becomes smaller. When the object is closer, the focal length of the eye lens becomes smaller. Hold on. If the focal length becomes smaller, what happens to the power? Bigger, because power is the reciprocal of focal length, right? So remember, when you're looking at objects that are close, that's when the eye lens becomes thick. Thick means the focal length is smaller. That means the power is big. And when you're looking at distant objects, the eye is relaxed. Okay? So remember that. That's why it says here, for those who like to read, the power of the lens of an eye is adjustable to provide an image on the retina for varying object distances. See that? So the object distances change, the lens changes by action of the ciliary muscles, the lens changes its focal length, and all this happens automatically. So here you have a person looking at a tree. And like we discussed, the image, what did I do? The image is going to be inverted on the retina, isn't it? You see that? You see that there is a small bending, actually a bigger bending at the cornea, and then again a bending when it passes through the lens, and finally you get the image, inverted image on the retina. And then, as you know, the brain flips it, and so you see it upright. So that's what happens. And remember that this distance between the lens and the retina for a normal adult is 2 centimeters. Good point to remember. It's 2 centimeters. Now, what would that distance be? Would that be the focal length? Would that be DO or DI? DI. So remember that DI is fixed. For a normal eye, DI is always how much? 2 centimeters. Good point to remember. DI is fixed. Does DO change? So does F change? Yes. So let's work out a simple problem and find out if the object is at the least distance of distinct vision. What is that? Anybody remembers the least distance of distinct vision? When I told you,
You can see.
yeah, how close you can see clearly, correct. And it's about 25 to 30 centimeters. So let's take it as 25. So somebody is reading a book, holding it at 25 centimeters. So DO is 25 centimeters, correct? DO is 25 and DI is 2 centimeters. So can you please calculate the focal length of the eye lens and the power of the eye lens? The focal length and the power of the eye lens. Remember, here we are assuming that the cornea does not do anything. See, we are assuming that all the refraction is by the eye lens. What should be the focal length and what should be the power? Is the question. But meanwhile, please focus on this. Now, this is what we just talked about. Relaxed. Oh. What do you mean by saying that the eye is relaxed? Where is the object? Infinity. That's what this diagram shows. Infinity. All right, hold on. Look at this diagram and tell me what's the focal length of that lens. 2 centimeters. Thank you for those who are listening. Because when the rays are at infinity, they are parallel and they come to focus, correct? All right. So when you're looking at objects that are close, it's called accommodative vision. You see the two words? Relaxed, you're looking at objects far away. Accommodated, you're looking at objects that are really close, maybe at the near point. That's the second diagram. If you take a look at the second diagram, you see that the object is very close, like at 25 centimeter. And you also see, watch this carefully, a parallel ray has to pass through the focal point, isn't it? So isn't that the focal point? Come on. Parallel ray, when it falls on the lens, and actually it's not parallel on the lens, so that should be approximately the focal point. But anyway, the focal point is not on the retina as in the last case, is what I'm trying to say. The focal point is not on the retina, it's somewhere here. You see? Anybody with me? Somewhere here. So what happened to the focal point? Did it become smaller or larger? Smaller, which means the power became bigger. That's what we showed in our calculation. Remember the numbers? It was 50 diopter and 54 diopter. Do you remember? I'm trying. It was 50 for a relaxed eye, and it was 54 for the accommodated eye. So you see that in the diagram. And so it should be very clear. That's why it says, when you look at objects that are closer, here I'm trying to get you the conceptual questions. A more powerful lens is needed. When you look at objects that are close, the power of the lens is bigger, right? 54 in our example instead of 50. Now, what happens? These are the answers to your questions. Look, if the lens is too strong, wouldn't this happen? Come on. The lens is too strong. What type of lens is this? Concave or convex? It's a convex lens, and if it is too strong, means it's more powerful, then its focus is closer, right? That's what you call myopia. So one reason for myopia or short-sightedness is the lens is too strong, or the eye may be too long. Look at the shape of the eyeball. Now, so there are two reasons for myopia. Number one, the lens may be too strong So the focal point is before the retina, or the eye is too long, see, elongated along the x-axis, see that? So again, the focal point is in front of the retina. But on the other hand, when you look at hyperopia, the lens is too weak. Therefore, see the focal point? It's behind the retina. That should make sense, is it? Too weak. So it's behind the retina. Or the eyeball is too short. So you can see it's like compressed along the x-axis. So once again, it's behind the retina. Now, I do not know if there's another diagram. There should be, but nevertheless, tell me, what kind of lens can we use to correct myopia? Remember that the lens is too strong. It's a convex lens, which is too strong. So you want this focal point to go back to the retina. Correct? So what type of lens would you use here? Concave lens. That makes sense because this is a too strong convex lens. So put a concave lens in front. Wear glasses that are concave, made of concave lenses. So you push this back onto the retina. Now come here. When you talk of hyperopia, the lens is too weak. So what would you do? Put a convex lens. So you converge it further and bring it onto the retina. Easy to understand. Now that's what is shown in these diagrams. This is what we talked about. So if you have a concave lens, you can correct myopia. And if you use a convex lens, you can correct hyperopia. It's very clear from that. You see that? That's how it's corrected. Sometimes the words nearsighted and farsighted are used. What's nearsighted? Myopia. Nearsighted, myopia, short sight. Near, short. So nearsighted is short sight. Farsighted means long sight, hyperopia. So don't get confused on those terms. It should be very clear. Let's see how you cannot get 100 on exam 4, okay? LASIK surgery, what do they do? Change the, where? Which part? The cornea. And actually they don't try to change the outside part of the cornea. They lift the flap up and try to work inside so the healing is faster. So they cut that flap, lift it up, work on the inside of the cornea, and then cover it up, you know, so for healing to be... Did you have it done?
Yeah.
It feels weird?
Yeah, like you could like feel the flap of cornea up on my eyelashes.
Correct?
It was so weird.
It is at that time, but later on it's better, right? It's good. Your vision improves. Of nature, most of nature is green. Trees, plants. You see that? So the eye is very sensitive to those, not to the blue color. So that's something.
So does that mean you can see more shades of green than like other colors?
Doesn't mean that you can see more shades of green. It means that if you have a mixture of colors, your eye would pick out the green faster than it does the blue. That's what it means. It's more sensitive. Pardon?
But what does camouflaging work?
How does camouflaging work?
Yeah, if you're sensitive to green, most of the camo is...
I mean, camouflaging also depends on how your circumstances are. Like if you're in the desert, then you need to wear something that is the color of sand. You know, so many other factors. But if you're fighting in Vietnam, then you obviously need to have the military uniform that we have. You know, just for lack of other examples. You know what? So camouflaging depends on, you know, how your surroundings are and you're trying to get there. So yeah, it has something to do with the sensitivity, but more to do with the surrounding. And I think I discussed this. I told you why an object looks blue in color. Why an object looks blue in color. White light falls on it, all other colors are absorbed, blue is reflected, correct? All right, same thing for the other things. I'm not going to spend time there. This one, emission spectra, I won't even talk about emission spectra and all that. See, now I'm being a cool professor, see? And I skip through slides. Then we go to a microscope. You may have a question on your final exam where you have to draw something. Draw something. Image formed by a convex lens, real image, virtual image. I'm telling you. Or refraction. Or bigger chances of drawing the image of a microscope. Okay? So I'm almost giving out the question. Microscope. A microscope has two lenses. One is called the eyepiece. That's what you look through. And the other is called the objective, which is what is close to the object, the slide. Okay, so a microscope has two lenses. One is the eyepiece, through which you look. The other is the objective, which is very close to the slide. And the distance between the eyepiece and the objective can be changed. Obviously, that is what you do when you focus. When you focus, you hold a knob and turn it. What are you doing? You are actually changing the distance between the eyepiece and the objective. That's what you're doing. Because they are in two tubes, one tube going through the other. When you change that distance, it's going to get focused.
So you don't move the objective, right? Like once you set the lens, it stays, and then you move the eyepiece to find the image?
Yeah, you could be. I mean, the mechanism could be either way. It's always easier to move the eyepiece because the objective is, you keep the slide very close to the objective. So if you move the objective, it's going to go hit the slide. So what you try to normally do is hold that objective there and move the eyepiece. But what's important is the distance between the objective and the eyepiece needs to be changed. But the rest of the story can only happen when you look at this diagram, which is really interesting. Let us look at that. Okay. Now look at the eyepiece and the objective and try to understand this. There is a 75% chance that this diagram will be asked. You have to draw it. And you have to practice drawing it. But first you have to understand. So the eye is there. You see that beautiful eye there. And look at the object. The object is very close to the objective. But I want you to notice something. The focal length of the objective is FO. The object must be kept just outside the focal length. All right. The object must be kept just outside the focus of the objective lens. Very important conceptually. And I want to ask you, if you have an object outside the focal point, do you get a real image or a virtual image? Thank you. You get a real image. Now, that's why you see three rays. We only needed two, but there are three rays. The parallel one is passing through the focal point of the objective. As you can see, this ray is passing through the optic center. What happens? If it goes through the optic center, what happens? Nothing happens. It doesn't bend, so it goes through, and then you have a third one. They all meet here, so it's a real image. You see that? That's the real inverted image produced by the objective. Now, you also notice the the focus of the eyepiece. Do you see that? The focus of the eyepiece. This image has to fall inside the focus of the eyepiece. So the image formed by the objective has to fall inside the focus of the eyepiece. And this image is going to act as the object for the eyepiece. I'll say that again. So the image produced by the objective is going to act as the object for the eyepiece. And since it's inside the focal point, what kind of image will you get? Will you get real or virtual? Virtual. That's why these rays, when they continue, you see that's the part you have to draw and train yourself to draw. They are diverging. You see that? They do not meet. So now you have to extend all three backwards, and they appear to be coming from here. Therefore, the eye sees a highly magnified image, an inverted image. See that? Highly magnified. So what's important is 2 or 3 points I'm going to summarize. Number one, the object must be kept just outside the focal point of the objective. Number two, the image produced by the objective must be inside the focal point of the eyepiece. Number 3, the image by the objective acts as the object for the eyepiece. All right? And continuing, you know that magnification, how is magnification defined as? Magnification has 2 formulas. Magnification is what? HI by HO or negative DI by DO. Now, if MO is the magnification of the objective, ME is the magnification of the eyepiece, what is the total magnification? Think before you answer. So let's say the objective magnifies it 4 times and the eyepiece magnifies it like 5 times. So what's the total magnification?
20.
Thank you. It's not 9, it's 20. So the total magnification is not the sum, but the product. That should make sense because magnification is a ratio. See that? So remember that always. Conceptual question. Be careful there. So that's about the microscope. Aberration means a defect. Now lenses. Lenses could have 7 types of defects. 7 types of defects. Don't worry, I'm not going into all those defects. There's only one that you have to know. It's chromatic aberration. Word chrome means color. So chromatic aberration means something to do with color. You know what chromatic aberration is? No. If you photograph a white object using a lens which has this defect, you will get an image like this. A white object, let's say a white piece of chalk or something, you will get an image which you would like to be white, correct? No, it won't be. It will be white, but the borders will have all the 7 colors. Violet, indigo, blue, green, yellow,